are Team 23050, the Rotating Detonation Engine Heat Management Team, and we are a group of aerospace and mechanical engineering students that simulated, designed, and tested a successful heat management system for Nobel's current RDE design. My name is Brianna Herman, and I am the team lead. The global energy crisis is one of the largest problems that is present today. In 2021 alone, the United States produced 2.7 billion metric tons of greenhouse gas emissions due to energy consumption. Through the use of rotating detonation engines, Nobel's mission is to more efficiently use fossil fuels to reduce these emissions. Theoretically, RDEs could increase fuel efficiency up to 25% due to its increased thermal efficiency. Not only does this increase in efficiency lead to a sustainable future, it is also extremely cost-effective. A 1% increase in gas turbine thermodynamic efficiency on a global basis is equivalent to $61 billion in capital costs to match the energy gain in 1% efficiency. So, what is a rotating detonation engine? Unlike typical engines which use a slow-burning deflagration to combust fuel, an RDE supersonically combusts fuel, rapidly increasing the pressure and temperatures within the combustion chamber. In the RDE combustion chamber, a mixture of fuel is injected to the bottom of the combustion chamber, where it meets a single detonation from the igniter. The detonation creates a shockwave that continuously propagates around the annular combustor. These high temperatures and pressures generate thrust or drive a turbine. A major issue with these engines is heat management. Long exposure to these high temperatures cause detrimental effects to the RDE itself. Our mission is to create a heat management system within Nobel's existing RDE that is effective and durable, as well as collect data to support their developing RDE.
Hi, my name is Sean Harkins and I'm an aerospace engineering student. I will be taking you through the system requirements for our project. The main system requirements that we laid out include the categories of performance and design features. Our heat management system must be capable of allowing the RDE to run for a 10-second test duration, and the system must be able to perform for at least 3 test durations, all under the operational vibration of the RDE. The system must also be compatible with LabJack data acquisition devices and must be able to measure the temperature of solids and water during engine operation, as well as the flow rate of the water.
Hi, my name is Joe Reed, and I'm one of the mechanical engineers on this project, and I'll be going over the design. When looking at design options for cooling the RDE, we decided that we would use a liquid cooling system with a split path design.
So in this animation here, you can see the 2 independent flow paths that we've created. You can see how they flow through the RDE body. If you look closely, you can see the inlets coming in, flowing through the cooling chambers, and then out to the exits.
To prove out our design before building our final product.
So this is our final design iteration here. We have the RDE chamber, which was machined out of aluminum. You can see the copper tubing, which we upgraded from the high pressure silicone hoses. Here's the single inlet here that splits into 2 flow paths that travel through the RDE body where the heat exchange occurs, then converge to a single line, and then you have your exit here. We also have some instrumentation. We have thermocouples at the inlet and the outlet. That way that allows us to calculate the heat removed from the system. And then we also have some thermocouples around the RDE body at varying depths and heights to gather temperature data from there as well. And then lastly, we have the interface with Nobel's igniter that we use to connect to their current system.
Hello, my name is Nicholas Gross. I am a mechanical engineer on this team, and I'm going to be talking about the testing we did to verify our design. Starting with a brief overview of how tests went, we heated the RDE up with different sources of heat to a steady state temperature or for a set period of time. Once that was reached, we removed the heat source, allowing the temperature to drop back to an ambient equilibrium temperature, all the while collecting thermal data. This was done again, this time with water running through the cooling channels, and this was done to compare the thermal distribution of the RDE with and without the cooling system active. All of the thermal data was collected with this data acquisition system, as shown here with the LabJack and thermocouples running from the board to the RDE, and these are type K thermocouples. Here's an image of the thermocouples connected to the RDE body in and around it. Additionally, before each test, we performed a leak test to confirm that there were no leaks interfering with the cooling system. For the first round of initial testing, We heated the RDE up using 3 different sources of heat, the first being a coil and hot sand, the second a hot ingot, and finally using hot coals. For each of these tests, we placed the heat source directly in the center of the RDE. And with this random initial testing, we ran into issues of keeping the RDE hot enough for long enough. However, with this issue, we still were able to collect data comparing the cooling and non-cooling, which allowed us to confirm that our cooling system was acting as we expected.
For our propane test. Then about a week later, we integrated our combustion chamber to Nobel's ignition system and conducted a full rotating detonation engine test. Here you'll hear a first initial ignition test, followed by the full rotating detonation engine cycle.
Hi, I'm Richie. I am an aerospace engineering student, and I am the analysis lead on the project. I will be discussing the system verification, test results, and data. The system requirements were verified by 4 methods: T for test, A for analysis, D for demonstration, I for inspection. Shown here is the performance requirements, which were all successfully verified. Next, we have the design requirements, which were also verified as well. As for the interface features and requirements, and the standards as well. Next, I will be going over the cooling test results. The cooling test involved 2 trials. One, which was a run with cooling, and one which was a run without cooling. From a side-by-side comparison of the thermal data of both data sets, the red representing the test with no cooling and the blue representing the data with cooling, we can clearly see that our cooling system is able to function properly and reduce the temperatures experienced throughout the entire engine. This set of data shown here is the coolant temperature data. This quantifies the efficacy of the heat management system. Next, we will move on to discussing the test data obtained from the test performed. This will be the duration test, which involved collecting thermal data from the engine at 2 different durations, 10 seconds and 30 seconds.
For both trials, the thermocouple data for each depth is shown. For the 10-second run, the coolant temperatures for the inlet and outlet were used to calculate the energy removed from the cooling system. The same energy calculation was done for the 30-second test. Our cooling system ran for 31 seconds at 650 psi of air and 300 psi of hydrogen. This heat management system effectively cools the RDE while it runs, as well as rapidly decreasing temperatures to equilibrium within seconds after full engine tests. During the full engine testing, no internal components were damaged. Thank you for your time.